Example 2.1.5, write the following trigonometric functions in exponential, angle, and rectangular phasor form. V is equal to 170 cosine of 377t volts, and I is equal to 10 sine of 1000t plus 20 degrees amps. And in part B, we're asked to write the phasor expression for V is equal to 20 at an angle of negative 15 volts in the time domain form. So the given information to us for part A is that V of t is equal to 170 cosine of 377t volts, and I of t is equal to 10 sine of 1000t plus 20 degrees amps. And then for part B, we are just given that V, notice it's a bold, so that's a vector, 20 at angle negative 15 degrees volts. So we are then asked to write these in exponential. So the form of exponential is V e to the j theta. Angle is magnitude of V, angle theta, or I'll use phi, be more consistent, and then V real plus JV imaginary. So we're asked to put that in exponential form, angular form, and rectangular form. And then, sorry, this thing's pretty touch sensitive at the bottom. The laptop, I mean. And then in B, we're asked to find V of t. So the solution for this is, we know that the form that we, in power systems that we want to write, the exponential form is that we write the RMS voltage e to the j phi. So we just need to come up to these and extract that information. So we know that the peak value of the voltage is 170. So V RMS is equal to 170 over root 2. That gives us 120, not 220, 120.21 volts. There is no phase shift indicated in this, so phi is equal to 0 degrees. Combine those together, and we get that the voltage phasor in part A is equal to 120.21 at an angle of 0 degrees volts. I can just go ahead and immediately convert that to the exponential form. V is equal to 120.21 e to the j 0 degrees volts. Very easy to convert between those two. To put that in rectangular form, I just need to use the law of cosines, or the definition of cosine really, and of sine. And I know that the real portion of the voltage is going to be given by the magnitude, 120.21, times the cosine of 0 degrees, which is equal to 120.21 volts. And the imaginary portion of that voltage is going to be equal to 120.21 times the sine of the angle, which is just going to be equal to 0. So if I want to put that voltage in rectangular form, it's going to be 120.21 plus J0 volts. That's not degrees there, that's 120.21 plus J0 volts. That's the real portion, that's the imaginary portion in rectangular form for the voltage. These two forms are very, very common. It's what you'll be using for the majority of the work in your class. This form of the voltage has some applications in power systems, but very few. But I did want to show you just how to convert between the voltage in angular or exponential form and rectangular. And a lot of times that's quantified as a triangle. Doesn't make a lot of sense for this voltage. I'll do it again for the current here. So for the current waveform, we know that the RMS, the RMS current is going to be the peak current over root 2. So that's going to be, if we come back up to our equation, we know that's peak current right there, 10. It's the amplitude of the waveform, so we get 10 over root 2 is going to give us 7.07 amps is the RMS current here. So we need to be a little bit careful. We see that this thing was specified as sine, not as cosine, so we need to convert from sine to cosine there. So I'll do that step next. I know that the sine of 1000t plus 20 degrees, I believe was what the problem statement said. That's going to be equal to cosine of 1000t plus 20 degrees, and then to convert from sine to cosine, I need to subtract off 90 degrees. Cosine leads sine by 90, so subtract that off, and I get that this is going to be the cosine of 1000t minus 70 degrees. Remember, we're always dealing with cosine waveforms in this class. If I try to trick you by giving you a sine waveform, you now know subtract 90 degrees to get it in cosine form. It's a common mean trick that faculty play on students, put it in sine form, so watch out for that. So from that, I know that the angle of this waveform is equal to negative 70 degrees, not plus 20 degrees, right? So that's where that trick comes in. I can write the current phasor I, that's now going to be the RMS 7.07 at an angle of negative 70 degrees amps, and that's going to be equal to 7.07 e to the minus j 70 degrees amps. Very easy to just convert between those two again. The real portion of that current is going to be equal to 7.07 cosine of minus 70 degrees, and that's 2.42. And the imaginary portion of that current is going to be equal to 7.07 times the sine of negative 70 degrees, and that's going to be minus j 6.64. And so the voltage in rectangular form is going to be 2.42 minus j 6.64 amps. And so this gives us a little bit better description in triangular form. We know, well, I drew that the wrong way because this is in the negative imaginary axis. So remember, this axis here represents the real portion. This axis here represents the imaginary portion, positive in this direction, negative in this direction. And so we know that the length of this vector right here is 7.07 amps. We know that the angle formed here is negative 70 degrees, and that means the distance from here to here is 2.42, and the distance from here to here is 6.64. So we just use the definition of the right triangle right there to make those relationships clear. So I imagine this is all pretty much review for you all at this point, so I'm not going to dwell on that. Part B, we were given 20 at an angle of negative 15 degrees, and we were asked to write the time domain expression from that. So remember, in this class, typically that 20 is the RMS value. 20 volts is equal to VRMS. When I'm writing the time domain expression, though, I'll use the peak value. So V peak is equal to root 2 times the RMS value. So that's root 2 times 20. And that gives me a value of 28.28 volts for the peak value for this waveform. I also know that from this statement that phi was just given to me directly. Phi is equal to negative 15 degrees, and so I can go ahead and write V of t from that information. That's going to be equal to 28.28 volts times the cosine of omega t minus 15 degrees volts. So I want to note a couple things about this answer. One is that I don't have anything in here for omega. That's because the phasor form here in either, I lost my little highlighter. The phasor form here, either in angular form or exponential form, does not give you any information about the system frequency, so I can't tell you what that is right now. So that's important that that stays omega, and I didn't put a number in there. The other thing that's interesting is, remember, omega, the way that I've written it, is usually specified in radians per second times in seconds, which means the multiplication of those is going to come out to radians. But this is 15 degrees. So since those two are added together in the argument of this cosine function right here, they need to be in the same units of angle. And so they either both need to be in radians or they both need to be in degrees. And so very typically what we'll have to do is we'll have to convert this 15 degrees over to radians by using the relationship 2 pi radians is equal to 180 degrees. So this is used really commonly. I don't know why it is so common in electrical engineering to give the angle of voltage phasors in degrees when we almost exclusively use angular frequency in radians. It doesn't make sense to me, but that's just the world that we live in. So be careful. Don't make the mistake of trying to add those two numbers together. Your calculator will not catch this problem for you. So you need to be diligent and make sure that the units that you're using inside the argument of your trigonometric functions are consistent with one another. I can type in, 2 pi radians plus 15 degrees, and my TI-89 is not gonna spit out an error message for me. Garbage in, garbage out kind of stuff right there. So just be cognizant of that.